As per our discussion in chapter 5, we have the phase diagram. However, in chapter 5, we only consider the phase diagram of a pure mixture, which is the C. If we refer back to the phase rule, F equal to C minus P plus 2, our components equal to 1 for chapter 5, where we only have a pure component. However, in this chapter, we discuss about the component or the mixture or the solution that have more than 2 components. For example, ethanol plus water. And in this topic, the composition is now a variable. The component is now a variable in addition to the pressure and also temperature. So in this chapter, we will see a phase diagram of mixture, which is the temperature composition diagram. So we will see a 3 type of diagram, which are volatile liquid, which is both of component is admissible. For example, ethanol plus water. Also, we will see a liquid, partially miscible, such as water and oil, partially miscible, and also we will see a liquid solid, which is a balanced system, which are independent, which is it's not soluble at all. And in a volatile liquid, miscible, we will see the diagram of a low boiling point is azeotrope, and also high boiling point azeotrope. First, we will consider the phase diagram of a binary mixture of two volatile components. This kind of system is important for understanding fractional distillation, which is widely used technique in industry and the laboratory. Intuitively, we might expect the boiling point of a mixture of two volatile liquids to vary smoothly from the boiling point of one pure component when only that liquid is present to the boiling point of the other pure components when only that liquid is present. For phase diagram of a mixture of volatile liquid, we see that both liquids are miscible. Both can be mixed in all proportion, so there will be no distinguished layer that we can differentiate which component is miscible, which are not. So for the characteristic of this mixture is one component of the mixture is more volatile than the others. That's why we can use a fractional distillation. In a fractional distillation, the boiling and condensation cycle is repeated successfully. Because this technique is used to separate volatile liquid. Because when we have two mixtures that is miscible in the component in the solution and mixture, if we compare the physical characteristic of the two components, or either one have more volatile liquid. So by using the fractional distillation, using this fractional distillation apparatus, what we can do, we can provide the heat. So the volatile component will be vaporized, and then when we put the cold water here, the water inlet and the cold water outlet, what will happen is it will be condensed, and we can collect our mixture that is more volatile, and what left is the homogeneous mixture, which is less volatile compared to this one. As per diagram is the process, a temperature composition diagram for binary mixture of volatile liquid. So the process of fractional distillation can be represented by a series of steps on a temperature composition diagram, as per figure. You can see from the figure that the initial liquid mixture may be at a temperature and have a composition like that, represented by point A1. It boils at the temperature T2, and the vapor in equilibrium with the boiling liquid has composition A2 prime. If the vapor is condensed to A3, or below, the resulting condensate boils at T3, here T3, and give rise to a vapor of composition represented by A3 prime. As the succession of vaporization and condensation is continued, the composition of the distillate moves towards pure A. And if we draw the line between A2 to A2 prime, this line joining two faces that are in equilibrium, same goes to A3 to A3 prime. This tie line is a line that joining two faces that are in equilibrium, and for this it shows that the vapor is richer than the liquid. Many binary liquid mixture do have the temperature composition diagram resembling that shown in this figure. So, and again, we can follow the change that occur during the fractional distillation of a mixture of a volatile component. By following what happens when a mixture of composition is heated, as for this diagram, when a mixture of a composition is heated, the mixture boils at A2. So this line is boiling temperature of liquid, while this line is a vapor composition of a liquid. So when a mixture of a composition A1 is heated, the mixture will boil at A2, and while the vapor composition has a composition at A2 prime. And this vapor condensed to a liquid of the same composition when it has risen to a cooler part of the fractionating column. And then this condensate boils at the temperature corresponding to the point A3 and yields a vapor of composition A3 prime. This vapor is even richer in the more volatile components. The vapor condensed to a liquid that boils at the temperature corresponding to the point A4. And then this cycle will be repeated until almost pure A emerge from the top of the column. Although many liquids have temperature composition phase diagram resembling the ideal version, however, still there is a number of liquids that is deviate from ideality, such as low boiling point azeotrope and high boiling point azeotrope phase diagram. So here is the low boiling point azeotrope, and this is the high boiling point azeotrope. Hence, if a minimum boiling point curve occurs in the phase diagram, interaction between A and B molecules are unfavorable. The mixture is more volatile than ideal mixture. However, when a maximum boiling point curve occurs in the phase diagram, interaction between A and B molecules are favorable. The mixture is less volatile than the ideal mixture, and the azeotrope is a mixture of two miscible liquids that when boiled produce the same composition in the vapor phase as that is present in the original mixture. Hence, the distillation process or distillation technique cannot separate the two liquids because the vapor and liquid have the same composition.